Okay, this is a video on sequences. Going to cover both arithmetic linear sequences and quadratic sequences. Not in this video geometric or recursive sequences. See another video for that. This is useful for GCSE, certainly the arithmetic linear, IGCSE. Specifications tend to have quadratic, and both of those are in A level, so it could be applied to A level, although you might need a little bit more depth in terms of some of the problem solving that you will do for A level. Okay, so what do we mean by all this? Typically, a sequence is something that we can define it in terms algebraically, and we'll use that algebraic expression in order to calculate the first, the fifth, the seventh, in general the nth term. So we often see these written in terms of n. Let's have a look at this one. Here are the first 5 terms of an arithmetic sequence: 3, 9, 15, 21, 27. Okay, well, before just doing that, let's just have a look at this one: 6, 12, 18, 24, 30. Now, if we look at this sequence here, then we need to notice that actually the difference of each between each term is actually 6. It goes up in sixes. And in fact, the first term is 6, the second term is 12, and then third term is 18, and so on. So this sequence, actually, we could actually just calculate this sequence as 6n. So we just substitute the number of the term, the fifth term would be 5, in there for n, and we would get the appropriate term. So 6 times 5 is 30. That's the fifth term. So that works fine. Now, this particular sequence, 3, 9, 15, 21, 27, is actually similar to this one on the right here. Just going to pointer. It is similar, but it's actually 3 less. So if we were to calculate the nth term of this sequence, then we could use the 6n as long as we subtracted the 3 from it. And in fact, if we try this out, we can see that this actually works. So, for instance, the fourth term of this 6n minus 3 would be 6 times 4 minus 3. So that's 24 minus 3 is 21. That's what we've got here. And of course, we can use this therefore to calculate, say, the 100th term. So that'd be 6 times 100 minus 3, 597. Okay, so that is kind of what we mean, and this is one way that we can actually calculate these linear sequences. So if we know that the differences of each term are a fixed amount, then we can use that fixed amount for our n, and then we can basically just do a bit of algebra or a bit of trial and error to find out what this constant term is here. This particular question goes on to ask a supplementary question. Ben says that 150 is in the sequence. Is Ben right? Well, we don't really want to keep writing these down and see if 150 happens to fall in it. It's a little bit easier than that. If the sequence is 6n minus 3, okay, then this term must be 6n minus 3 for some value of n. So 6n minus 3 is going to be equal to 153. So therefore 6n must be equal to 153 for that value of n. So in other words, 153 has to be a multiple of 6. If it is, it will be in the sequence. Okay, well, I'll leave you to work that out. This is the sort of thing that you get from getting these questions. Let's have a look at this one. A little bit more to this one. Here are the first 5 terms of an arithmetic sequence: 4, 9, 14, 19, and 24. Find, in terms of n, an expression for the nth term of this sequence. So similar kind of question, really. So what are we looking at? The differences here, I think we can see the difference between each term is 5. So it's going to be, there's going to be a 5n term in there. And now d, we often use d to denote the actual difference. We'll come to that a bit more in a moment. So d is 5, so we know it's going to be 5n plus some constant k, which may be positive or negative. Right, so now we just have to kind of work out, well, what would happen for the first term? For the first term, we would have 5 times 1 plus k. Yeah, 5n plus k. Evaluated for 1, 5 times 1 plus k is going to be equal to what we've got here is 4. Okay, so we can just work that out. K is equal to -1. So this is going to be our expression here. And we can perhaps just check this. What happens? Well, we got a fifth term of 24 here, so that should work out. So if we put 5 in for n, 5 times 5 is 25 minus 1 is 24. So it works for that term. So, you know, I think we can take that as being read. Now, there are some formulas here that are kind of interest. So sometimes we write the nth term as un, as here. A is the first term, n is the number of the term, and d is the difference as per here. So we could say for this one, we could actually use this little formula instead of using this method here, where we sort of just formulate it in kind of steps like this. So yeah, so what would happen if we're looking for the nth term? Un equals 4, that's the first term, plus n minus 1 times 5. So when you work that through, that's going to be equal to 5n minus 1, which is good, because that's exactly what we got using our other method. All right, so that's a way of doing it. Now, it's more to do with A level, really, but kind of worth knowing, really, is that sometimes what we want to know is we want to know the sum of a sequence of terms. So in this case here, this is simple. You could add it up in your head, really, couldn't you? But it gives us a way of adding these up. Obviously, we're looking at 100 terms, then we don't want to be adding them up in your head. So these formulas can be useful. So the first formula basically says the sum of the first n terms. We can use the first and last term. So if we take the number of terms that we're interested in, and this starts with the first term, divided by 2 into the first term plus the last term. So here we go. Let's just do it for this thing that with this sequence we've got. So the sum is going to be equal to the 5 terms divided by 2. That's the first term, 4, you can see from here. And the last term is 24, that's up here. So just work that through, and that gives you 70. So that's quite good. And I mean, when you think about this, this is a little bit like think about geometry, about the area of a trapezium. Okay, I'll just put that thought in your mind as to what we're doing there, but there's a little bit of a relationship there. There's another formula here, which is not in terms of the last term. Essentially what we do is calculating the last term and then substituting it into this formula here. So you can see here, one of the a's is the first term, and then the other a plus n minus 1d is this. So it's kind of fairly straightforward bit of substitution. So we can just use this, and we can try that out. I've done it there. We get the same answer, 70. So just 2 different ways of doing it. Now, I'll say you may not need to do that at GCSE, possibly to IGCSE, but it's not that difficult, really, is it? So that's worth putting in. Let's have a look at this one. Here are the first 5 terms of an arithmetic sequence. 7, 10, 13, 16, 19. Find the sum of the first 100 terms of this sequence. So So, right, well, we're going through our little process. We can either use this first, let's just first little formula here, or we can use the initial method. We know that, it's going to be 3n, and then we can work out from there. It's 3n plus 4. Okay, find the first 100 terms. All right, so yeah, which of these are we going to use? Well, let's use this one. It builds in our calculation of the last term into it, so it does kind of save us a step, really. So the sum is equal to the number of terms divided by 2, 100 divided by 2, plus twice the first term, that's this one, plus n minus 1, well, n is 100, isn't it? So that's 99, times the difference, which is 3. So that gives us that expression. And if we multiply that out, we're going to get 1550, 1550. So that is the sum of the first 100 terms of that sequence. Right, good. Okay. Let's just for a moment think about having a quadratic in there. I'm gonna do more on this in a moment. But the nth term of a number sequence is n squared plus 1. So if we work out what those terms are, that's the first term, second term, third term, fourth term. Yeah, so it's n squared plus 1. Well, if n is 1 for the first term, then that's 1 squared plus 1, that's 2. Second term, 2 squared plus 1 is that's 3 squared plus 1, and that's 4 squared plus 1. Now, if we look at the differences of this sequence, we find that actually they're not the same. That's not surprising because it's not a linear sequence. It's linear if we just have an n term, but no n squared term. It's 3, 5, 7. So these are actually increasing. Now, and that tells us basically, it's not linear. But if we take the differences of the differences, so let's have a look at the difference between these two, these two and these two. That's 2 and 2. So that tells us we're basically dealing with a quadratic sequence, and the 2 actually means that we've got an n squared term. We're basically half the 2, and it tells us we've got an n squared term. Okay, so so that is what we're looking at. If it was 2n squared, then those differences would go up. The differences of the differences would go up by 4 each time. So we can just halve that, and that will tell us what our n squared term is. All right, so now just hold that thought. We're just basically going to have another look at a linear sequence, and this is simply because this is more like the kind of problem you may get. It's a little bit more sort of a bit less mechanical, and you put a little bit more thought into it. Mario is going to save $50 in the year 2021, and then he's going to continue to save up to and including the year 27 by increasing the amount he saves by each year by k. Well, we don't know what k is at the moment. But if we now what we should note here is that this is 50 years. He's going to do 50 years worth of saving. Yeah, so that's always important to know with these kind of questions. So if we just write that out, or write out the first few terms, you can see in 2021 he saves 50. 2022 he saves 50 plus k. 2023 is 50 plus 2k, and so on. All right. So the total amount he's saved in those 4 years is going to be, well, 4 lots of 50 plus a k, a 2k, and a 3k, a 6k. So it's going to be 200 plus 6k. Now it does say that Mario will save a total of 33,125 in those 50 years from 2021 to 2070. Okay, so they've given us, going back to our previous formulas, they've given us the sum, the s subscript n, s sub n. So what we have to do is formulate an equation. So this basically is, you know, he's giving us an indication of what the equation is. So the sum over the sum of the sequence is going to be the number of terms. This is going to be 50, isn't it? Divided by 2 into the first term plus the last term. Right. Well, what is the last term? Well, just following this pattern through, I think we can see 2070 is going to be 50 plus 49k. Okay, so if we carried on these dots and got to 2070, we would it would be telling us that would be 50 plus 49k. That is our last term. Okay. All right, so let's just plug in what we know here. N is 50. The first term is 50, and the last term is 50 plus 49k plus 49k. This one. All right, so and that sum that we know, because they tell us, is 33,125. So our equation is 33,125 equals 25 for this 50 over 2 plus 100, some of those plus 49k. And so simply we can just go through and solve that for k, and that gives us a k of $25, which is what they're asking us for there. Okay, so that is sort of a more problem-oriented question with sequences. Okay. Right, so let's go back to quadratics now. Write down the next two terms in the following quadratic sequence. Well, if we write the terms there, we write the differences 4, 6, 8. I think pretty well we can see that the next two differences are going to be 12 and 14, and that 12 is going to take us up from 27 to 39, and the 14 will take us from 39 to 53. So 39 and 53 are the next two terms in this quadratic sequence. Okay, let's have a look at this one. The nth term of a sequence is this. Work out the 10th term. Well, we simply have to evaluate this with n equals 10. Pretty straightforward. 2 times 10 squared equals 4 times 10 minus 1. That's 239. So 239 is the 10th term of that sequence. All right, so far so good. Let's have a look at this one. Now this one's asking us to work out the formula for the nth term of the quadratic sequence. 2, 10, 22, 38, which we've got there. So I've done the differences. They're not equal, but the differences of the differences are 4. So that's telling us there's going to be a 2n squared term. Incidentally, it tells us it's a quadratic sequence, so you know, we know what process to follow. If it just said it was a sequence and these were the first 4 terms, there are other possibilities that it might not be a quadratic sequence. So we might find some formula which predicts the 5th term to be something, but it might be something else. So, you know, there might be following some other pattern, but this says it's a quadratic sequence, so that's fine. So we know that the differences of our differences for there is going to give us this 2n squared. So it's going to be 2n squared plus something n plus some constant. So how do we find the last bit's just a linear sequence, isn't it? So if we could get rid of the contribution of this 2n squared, then we'd just be left with a linear sequence. That would be nice and easy, wouldn't it? Well, of course we can do, can't we? Because we know exactly what 2n squared contributes into this set of numbers, into this sequence here. It contributes, let's work it out. If n equals 1, it's going to be 2 times 1 squared, which is 2. If n equals 2, that's 2 squared. 4 times 2 is 8. For 3, it's 18, and for 4, it's 32. So this is the contribution from that 2n squared part. So if we strip that out of this, the original sequence, then what we're left with is just the linear sequence. something n plus some constant. Okay, and that linear sequence is this 0, 2, 4, 6. Pretty straightforward, I think. It's got differences of 2, so we know we've got a 2n there. Okay, so for the first term is going to be 0, so we can conclude from there that k is going to be minus 2, 2n minus 2. Okay, let's just check that for let's say the third term. 2 times 3 is 6, minus 2 is 4. That's what the third term. So we're happy with that. So therefore we know that the quadratic part is this, the linear part is this. We can glue them back together and we get 2n squared plus 2n minus 2. And were we to stick 4 into there for the n, in that expression, then we would certainly find that that equals 38. So that's basically how we sort of unpick these quadratic sequences, is find out what the n squared term is, strip it out of the sequence, and that just leaves you with a linear sequence. Okay, so basically that is that's it. I think hopefully that's given you an idea. There is more on this in the A-level videos. So this could be an introduction for you for the A-level videos. But if you do the A-level videos, then you're often finding that you have to form simultaneous equations. They'll give you a couple of facts about the sequence and ask you to work out maybe the first term and the difference or something along those lines. So there's a bit more complexity in some of the questions, and you might find that there are more sort of narrative-based questions in there as well. But at this stage, really that should stand you in fairly good stead. If you understand what's going on there, then you should really be able to have a go at most of the stuff that comes up in GCSE or IGCSE questions. So hopefully that's been useful. Thanks for listening.